Thank you again, Steve. I appreciate this opportunity to talk to the international group of HGS. And as you're all aware, being geologists or geophysicists, but geologists, geophysicists, geoscientists, we have a pretty comprehensive understanding of Earth systems and the technology that we use to image those systems and understand those systems. So tonight, I'm going to familiarize you with the program Geosciences Without Borders that I've been working on for the last couple of years on the committee with Mike Forrest. And it was created to apply our knowledge of Earth systems to humanitarian needs in communities around the world, while simultaneously training a new generation of geophysicists around the world, in the US and globally. Geosciences Without Borders. It was started in about 2008 by Craig Beasley and other SEG members. They had the generous support of Schlumberger, a very strong support from Schlumberger. So the mission of Geosciences Without Borders, as it was originally defined, and still is today, is to support the application of geoscience knowledge and technology around the world. And we're different from some other groups in that we actually fund projects to benefit communities, and that the communities in need due to environmental hardships, natural hazards, natural and human-induced disasters, as well as the opportunity. We saw it as an opportunity to train new geoscientists. GWB, as we call it, is managed by a steering committee of the SEG. And since 2008, in the last 10 years, we've awarded about $2.6 million for projects. This is the committee as it currently exists. Mike Marianic is the chair. You can see several companies, oil and gas companies, as well as some engineering companies that are involved here. Susan Gans from Schlumberger, Isabel Lambert from CGG, Nick Lagriere from Merrill, Doug Lehman, Collier Consulting, Phoebe McMillan at Elsevier, myself, Richard Nolan Hooksma, who is here tonight with Darcy Partners, and Greg Parker at PGS. So I think of Geosciences Without Borders as having three legs. Number one is the humanitarian need, solving those problems. Number two, strengthening geoscience. And number three, education, particularly at the community level. So let's talk about human needs. What human needs are we dealing with? Well, it's water, quality, accessibility, and management, often with groundwater. Geologic hazards, volcanoes, earthquakes, tsunamis, landslides, floods. Then two areas that are often associated with food security. Soils, with respect to agriculture, and habitat management. It might be with fisheries, and I'll show you a project with fisheries. Next, strengthening geoscience. Well, how do we do that? Many of these programs, or most of the programs, are done with principal investigators from universities. They're designed as multidisciplinary partnerships. They looking at broadening the applications of technology, and finally training a new generation. And to give you a feel for how some of these projects are built, in the upper right here is a group of people who work on one project in Indonesia. Not only universities, and I'll talk about this project. This is the Java Tsunami project. Community outreach. How do we get our message to the community? How do we get the community to understand the geologic hazards, or water management, or food security issues? This is building community outreach into the programs, working with local governments, and working with NGOs. So the program focus. Program focus really is to strengthen the geoscience applications through multidisciplinary projects. We want them to have humanitarian impacts, and we want to have them provide training. So we want students involved. We want to be sure that we can make a significant difference in the lives of those in need, particularly if we can make community improvements. We want to have collaborative project activities with local communities and local governments, as well as humanitarian organizations. And finally, we want to empower the community residents, the students, the scientists to work together and learn to share knowledge, share their knowledge. This is a list of projects around the world. I put this up to show you the variety, the numbers of countries. The ones in red here are those that I'm going to be talking about tonight. So as geologists, we always like to look at things spatially, and the world's a little dim on this picture, but you can see the red arrows and where the symbols are. So we've done 33 projects in 27 countries to date. That involves 14 universities and 14 non-US universities and NGOs. As part of the projects, we've involved 150 universities around the world, university and nonprofit partners. And we've had over 360 students involved in these projects. So we've had a pretty good reach. So now I'm going to go from this point, introducing GWB, and let's look at some of the projects. This first project is the Kakuma project in the Rift Valley of Kenya. Done fairly recently. It was run by Paul Baumann, who was with Worley Parsons in Calgary. The University of Calgary was involved. IsraAid was involved. The Kenyan Water Institute was involved, as well as students that are in the refugee camp. IsraAid runs a program there called WASH, which is Water, Sanitation, and Hygiene. The objective, so the Kakuma refugee camp has a population of over 200,000 people. Most of these come from southern Sudan. The program consisted of geophysical data acquisition and interpretation and water exploration. The work that was done was resistivity surveys, and you can see up in the upper right one of the resistivity lines, as well as some seismic refraction studies, and you can see some of the Kakuma refugee camp individuals helping us laying out cables. And the project impact. So we've talked about who did the project, what were the project objectives. Well, based on the work that the group did, they drilled the UNCOR, which is the Humanitarian Commission on Refugees. UNCOR drilled 3 successful wells with sustainable rates of between about 30 and 45 cubic meters per hour. UNCOR actually has a standard of practice, and they flow their wells for about 10 hours here. That 10 hours of flowing yields enough water for 57,000 people. And UNCOR assumes 20 liters of water per day per person. The good thing about this water is it's only 0.9 milligrams per liter of fluoride. And fluoride contamination is a problem in this part of Africa. The WHO guidelines are actually 1.5 milligrams per liter. As an outgrowth of the project, they identified additional locations. I don't know what the results or if they even drilled the wells up to those locations yet. But the real impact of this is that Paul Baumann and the group were able to document that they've got an application using geophysical technology and geology to apply elsewhere in the Kenyan Rift Valley to find good quality water. The next project is an earthquake project. This is a fairly early project. It was in Kingston, Jamaica. It was run by Matt Hornbach at Southern Methodist University. It included the University of West Indies, the University of Houston, and the UT Jackson School of Geosciences. The picture at the bottom here actually is a sketch of the results of the 1692 earthquake in Jamaica. That 1692 earthquake, as you can see, caused a lot of damage on land. I pointed this somewhere, but caused damage on land, as well as offshore. You can see lots of stuff floating in the water. That was a result of a tsunami. Another earthquake, another more recent earthquake was in 1902. So there's this periodicity of earthquakes in the Kingston area. Kingston itself is on, of course, as you know, is on the South Island, or on the south side of Jamaica. It's the longest inter-Geo plantain garden fault, and that fault is the one that was responsible for the movements in the 2010 Haiti earthquake. Kingston itself is the economic and political capital of Jamaica, has a third of the population of Jamaica living there. And it has shipping docks, refineries, power plants, a lot of infrastructure. So the objective was for the project to assess the future hazards of earthquakes in Kingston. What's going to happen? They wanted to determine the location of active faults. They wanted to determine the areas in the harbor that are most susceptible to earthquake damage, slope failure, tsunamis. Determine the sources of tsunamis, where these tsunamis originated. What's the frequency of large earthquakes? And then finally, at the bottom here, educate, inform, and work with the Jamaican government, industry, academia, to increase awareness that there are earthquakes in this area and there's potential damage, both earthquake damage and tsunamis. So this shows you a couple of images. This is a view across the bay into Kingston. They were able to identify this fault. This fault goes right into this power plant. This is Long Mountain. There's another fault here along the bottom of Long Mountain. On the right, we have the program they did in the harbor, and at the bottom, a sparkle line that shows the evidence for slumping here, another slump here, and chaotic reflections. This is 5 meters, so fairly shallow. So in the last 14,000 years, frequent slope failures, as well as potential evidence of tsunami deposits. So what's the project impact? Again, here we see Kingston, which the bay, where there's the harbor in offshore Kingston. We have Port Royal, power plants, Long Mountain over on the right. Well, the first thing we realized was that given an earthquake, there was inaccessible at the Norman Manley Airport, the principal airport. Bull Bay, which is about 4 kilometers to the east, would be inaccessible. You couldn't get from here to there. And Port Royal, out here where the Coast Guard is located, is inaccessible. Likely, there would be potentially severe tsunamis, particularly near Port Royal and Long Mountain, over on the right. We'd have, because of the power plants, there would be potentially long-term power loss, as well as hazmat issues because we've got fuel depots located along the coast here. The Coast Guard headquarters, the Navy Coast Guard headquarters would probably likely be crippled. And finally, in the loading docks, the container shipyard, there would be widespread damage because the faults go right into this area. So significant damage. They worked with the government to talk about these issues and gave them the maps and the evidence. The next project This is along the same Enrico Plantain Garden Fault that I just mentioned. That's the Haiti Subsurface Imaging Project. Can you switch those, Jim? So they're darker.
I'm trying.
Okay. Anyway, so Rob Stewart was the principal investigator in this project. There were at least 5 graduate students from the University of Houston, had the University of Calgary involved, SMU, the State University of Haiti, we had a number of students involved there, the Bureau of Mines and Energy, the Haiti Ministry of Economy and Finance, and then a couple of companies that either provided additional funding or actually equipment in kind. In the upper right, you see the island of Hispaniola. Haiti's on the left here. Whoop. I need the light just a minute.
That's it. You got it. Just got it.
That's good. A lot better.
Got it. Okay. This will work. So this is the island. Haiti's on the western end. We're looking at where this box is, a blow up of that. This is Lake Enriquillo. This is the Ilgan Delta. And then they did some work in between the two. Here's the Ilgan Delta. I'm going to talk about that a little bit more. And this is some of the work they did in Lake Enriquillo. What have we done?
I turned off the presentation.
There we go. Okay, back to the Ilgan Delta. They set up GPS stations and gravity and seismic surveys in this area. They identified evidence of faulting and damage. Here's some road damage that they identified. But what they determined in here, that this is an area with a blind thrust. There's no significant surface faulting as a consequence of the earthquake in there. In Lake Azui, which is just near the Lake Enriquillo, they did bathymetric surveys and ran about 94 kilometers of lines in the lake. They worked another small lake here, and it sharpened the understanding of the faults because this is a north-south or north-south seismic line. This is 10 meters. The line is located there. So if we start on the north side of that line, coming off of the anticline, it's here on the edge of the lake, coming into the basin, and there's a blind thrust here that they were able to identify. If we look on the south end of that line, we see coming into the lake, and it's pretty flat. This is only about 700 meters of sediment here. But you see a lot of breaks in the basement, and these faults come actually all the way to the surface. And right here in the middle, they're able to identify the Lake Enriquillo Plantain Garden Fault, so they could document that it actually goes all the way through here. So what's the project impact? First of all, as I said, there was no clear evidence of faulting in the Ilgan Delta. That damage was caused by uplift above the blind thrust and then subsequent shaking of the relatively weak sediments, seismically weak sediments. They successfully managed to trace the Enriquillo Plantain Garden Fault, identified evidence of recent faulting in the lakes along there, and in addition to working with the government, they involved, all the time they were doing this work, they involved villages along the way. So the local population, local communities knew what they were doing and how they helped them understand what was going on here. Now let's look at tsunamis. This is a project run by Ron Harris at Brigham Young University. It included 9 professors, 10 government officials, 30 students. Who was involved? Utah Valley University, in addition to BYU, and Bangkok University in Indonesia, the Institute of Community Development in Indonesia, the Indonesian Government Disaster Mitigation Agency, and the Indonesian Institute of Science. So this is the island of Java. The red here represents all those lands that are 20 meters or less above sea level. And I'll tell you in a minute why 20 meters becomes important. They did a series of reconnaissance sites. They collected samples in trenches along the coast in order to see if they could identify when the tsunamis occurred. And then they did presentations to communities and actually held evacuation drills. This 230 kilometers is important because the Java Trench is located along here. And for those of you who like equations, this happens to be the equation of the velocity of a tsunami. It turns out if you have a tsunami 230 kilometers offshore, it takes 20 minutes for the tsunami to be affecting the Java shoreline. And the 20 meters is important is because there's been almost no recorded and no historical record of a tsunami going higher than 20 meters. So, what was the objective? First of all, they had to look for evidence of tsunamis in the past, geologic past. There have been 105 historical records of tsunamis over the last 400 years in Indonesia. That means Indonesia averages one tsunami every 4 years. In the last 22 years, there have been 200,000 fatalities caused by 7 of 8 tsunamis. So it affects a lot of people, and there's 6 million people living along that coast of Java, the south coast. The questions that were asked are those in harm's way aware of tsunami hazards they face. As a matter of fact, the tsunami hazards and the historical record, they could find it in the historical record. Here we are looking at this cut bank, and these 2 black lines are shell hash and coarse sands from tsunamis, one at 1600 and the other one about 1800. So, if they're aware of tsunami hazards, do they know how to respond? And finally, what is the most effective way? They work with the communities. What's the most effective way to increase resilience to tsunami hazards in Indonesia? They went for looking at the historical record and ground truthing, because they did modeling of tsunamis, ground truthing their maps. They did trenching, ground penetrating radar surveys. So they did the tsunami inundation maps. And then they came up ways to communicate risk in a way that promotes preparedness and conducted the evacuation drills. These blocks here, these imbricated blocks, were deposited by a tsunami. And they extend inland here into the fields, actually. And here's Ron Harris communicating to a small group of people what he's doing, sitting there looking at those sediments. So how did they do this? After constructing their inundation maps, they knew where the problems could occur. So they held meetings with community leaders and citizens. And they gave this story to over 2,500 community people, citizens. They needed to develop the awareness of the risk, understand what the signs were, and how they would respond. And then, as I said, they did evacuation drills. Well, this is the way one community responded. After the team left, they had a parade. And then this parade, each of these bicycles is decorated as a tsunami. So it has a tsunami wave. Well, the way that they communicate this now is 20-20-20. If you feel an earthquake shake, or the ground shake for 20 seconds, here, ground shake for 20 seconds, there's a clock behind here, you have 20 minutes, that's the time it takes to get to shore, to get 20 meters above sea level. 20-20-20. Indonesia is now adopting this as one of their prime tsunami preparedness for disasters concepts. Let's change subjects a little bit. Let's look at landslides. This is a landslide project in Peru. It was run by the Institute of Science and Eric Laroche Institute of Science in France, the French Institute of Research and Development, University of Grenoble, the CNES, the French Space Agency, the Peruvian equivalent of Geological Survey in GEMET, the Peruvian Space Agency, CONIDA, and the community of Maca in Peru. Maca itself is located about 55 kilometers northwest of Arequipa. Arequipa is down here close to the coast. This is Maca. For your information, all these yellow dots represent earthquakes greater than magnitude 4. Around Maca, there's a series of landslides that are causing significant issues. Here's a picture of Maca. Looking to the south, this is the city of Maca, the township of Maca. The red line is the main scarp of the landslide, and you can see how it's starting to affect the village of Maca. Here are some pre-Inca terraces that have been damaged by movement, and I'll talk about these 3 inverted triangles here in a second that were placed there by the project. Another image, Maca is located in here, and this area of yellow indicated at least 3 meters of displacement since in between March 2013 and July 30th, 2013. The objective was to identify the scenarios for landslide development. When do these develop? And then, as an outgrowth of that, develop an alert system for the village of Maca. They wanted to understand whether these landslides accelerate from seismic activity or only periods of intense rainfall. They installed a permanent monitoring system. As an outgrowth of that, developed an alert system using GPS to track movement and seismic real-time observation to track movement. And in the process, trained local geophysicists within Peru to monitor these landslide parameters. They built three instrument huts like this, put in GPS equipment and a seismograph. The data is transferred in real time from Maca to Maca, as well as in GEMET, the Geological Survey in Peru, and ISTER in France. As a matter of fact, after they put this in, they found that there was a 5.4 magnitude earthquake that actually started that landslide moving again, and that movement continued on into the rainy season. What's the impact of this project? They found that this landslide monitoring is an effective way to provide a sustainable solution. They're not going to stop the landslide, but they can prevent damage to the community. It increases the capacity of the Peruvian scientific institutes to manage these natural hazards. They involve the local authorities, the pupils, and young people in the community. They were involved with the installation and actually involved with guarding. They understand the significance of these of these instruments and how important they are to the community. And the local authorities are involved both with the data transmission and interpretation. Changing subject again, and now we're going to look at some pollution issue. This was put together by the University of Bucharest. It involved several universities in Romania, the Romanian Society of Geophysics, Professor Uni, that provided a lot of the analyses, and the municipality of Metz. And there reportedly more than 40 students participated in this program. So where is this? Well, this is the Empua Valley in Romania. Zlatna is located here, the township or the municipality of Metz is located down here. Zlatna has been undergoing, is a mining district since at least 1347. And when they mine gold. Copper mining and silver and gold extraction has been occurring since the late 18th century. They had peak activity between 1970 and 1985, and that activity included both a smelter and a copper refinery. They felt that they understood that part of this valley was polluted. They wanted to identify the pollution sources and the distribution of pollutants in the soil and water. They did this using resistivity surveys, shallow reflection seismology, magnetometry. They dug 2 to 3 meter holes to examine the stratigraphy, soil chemistry, and water chemistry. So here they are laying out a line. Here's their seismic source, and this is one of their seismic lines that they used to identify the stratigraphy and where some of the deep, where the shallower aquifers were. The impact of the project documented that the water sources used by the local communities is contaminated, and deeper aquifers were likely contaminated as well. This is soil analysis of zinc and lead. This is a water analysis of lead, and this was the magnetic susceptibility. You can see that zinc, this is Zlatna is located out in here. Zinc, the reds are high pollutants, and interestingly enough, those zinc areas correspond with magnetic anomalies along the river. In terms of lead, the whole valley is contaminated with lead. Water analyses, you can see around Zlatna, high lead, and another point source down in this part of the river as well. So even the water has some lead pollution in it. So they talked with the local communities in the valley, worked with them, and these communities got together and were planning to develop an alternative source of potable water in 2012. Food security, benthic habitat mapping to improve fisheries and conservation. This was operated by University of Kentucky. Mike McClue was the principal investigator. It incorporated the Tanzania Fisheries Research Institute, Lake Tanganyika Authority, University of Wisconsin, University of Wyoming, Oklahoma University, University of Arizona, and the Nature Conservancy. This is Lake Tanganyika, and there are 3 yellow dots in here that represent the areas that they worked on. The objective was to develop a background to come up with a way to develop community-based fisheries management. This area, the fisheries in Lake Tanganyika are declining significantly. They depend a lot on these fish. So they recognize that the littoral and the pelagic fisheries are under pressure. That pressure comes not only from overfishing, it comes from environmental, it comes from development along, actually farming along the shores of Lake Tanganyika. That farming causes extra silt to come in. This is a picture here of the natural bottom, and you can see how little silt there is. When you get silt coming in, the fish lose their spawning places. And this is the surface in that area. They did this acquiring acoustical data, also sediment texture, sediment mixing, and accumulation rates. And what they focused on then is the bathymetry. What did the bottom look like? What was the substrate type? Is this silt or is this rocky? And what were the depositional dynamics? So they were able to compare the depositional dynamics of both the altered state and the pristine state. And out of that, they were able to come up with a program of small protected zones along the margin of Lake Tanganyika. So using the bathymetrics and substrate samples, they were able to establish these protected zones to help the fishery recovery, and they were working primarily in this Mahali region. Another aspect that we like as part of this funding program is they donated the geophysical equipment and books to FURI, the Department of Fisheries. And that makes the project sustainable. So now the fisheries could go in and continue this work along the margins of Lake Tanganyika, work on food security for the population around the lake. And the Nature Conservancy's involvement, because they've got a nearby project, the Nature Conservancy is helping to monitor the sites and help train the villagers. They've been working there a lot longer and conducting outreach and making recommendations for future work.
So they're basically to do land zoning and don't farm in this area? Is that what the protected areas are?
I think what the protected areas were areas without the farming. So if there is farming here, and they may work with the communities to do that. I don't know how far it's gone to that point. Let's see. Next is a volcano project. This was operated by Michigan Tech. Thomas Owen was the principal investigator. It included the Guatemalan seismic, volcanologic, meteorological, and hydrological group in Tsunamis, San Carlos University, particularly students from San Carlos University, the Instituto Geográfico Nacional in Guatemala, the coordinating group for disasters in Guatemala, Pacaya Volcano National Park, the U.S. Geological Survey, and the International Volcano Monitoring Fund. This is an image of Pacaya Volcano and what it looks like today. So how are we going to monitor these volcanoes? They needed to build, the objective was to build capacity to monitor both the eruptions and potential catastrophic landslide activities as a consequence of these eruptions. To do this, they wanted to establish a seismic monitoring network and set up a volcano monitoring camera so they knew when there was a volcano eruption occurring. Again, like the Pacaya project, they built these facilities here to hold the seismic graphs. And here's the inside of one of these installations, and here they're working on some of the instrumentation. The project, and most of the money for this project went into purchasing these seismic stations, seismic equipment. They established, so Pacaya Volcano is here, they established a seismic program there, one here, and one here. So those installations all have the seismic as well as GPS in them to measure any accelerometry. The data is transmitted to Tsunamis as well as to Michigan Tech. They established the webcam to monitor the volcanic eruptions on Pacaya. How do they communicate this to the general public? Well, working with Pacaya National Park, they developed a volcanic hazards display to help them communicate to the visitors to the park, as well as local communities what the hazards are. And an outgrowth of this project is at least 3 theses for students in San Carlos University in Guatemala. So now I've introduced you to GWB, Geosciences Without Borders. I've given you examples of several of our projects. Here's some of our donors. Schlumberger, as I said, was a founding supporter. Without Schlumberger and his initial funding, it it would have been difficult to put this together. But PGS has been involved, CGG, Kiwi Energy, Centos, and Global Geophysical. We also have societies that are helping support the programs. That's the AAPG Foundation, and we appreciate the AAPG Foundation for that. The Geological Society of America, and the Environmental and Engineering Geophysical Society. Several other corporate donors have been involved over the years, and there's been a lot of individual donors as well. So what I tried to talk about today is the global reach of Geoscientists Without Borders. And we're, together with Mike Forrest, we're trying to build a program to make these projects more sustainable in the future. In other words, we want this project, GWB, to continue. And so we're in the middle of a fundraising program for that. Those of us who are on the committee looking at the applications for grants would like to see more grants. And in conclusion, GWB was created, as I said, to apply our knowledge of the Earth systems to humanitarian needs in communities around the world, and while simultaneously educating a new generation of geoscientists. We think we've accomplished that to date, and we want to continue this into the future. Thank you.
On the floor. Mr. Tucker.
Yeah, Bob, this has been fascinating
Right, Jim.
since I first heard about it quite a while ago. So, do you need bodies or bucks?
Yes. We are, let's see, I think we're replacing 4 members of the committee this year. So we need committee members, and we need bucks. Martin?
I just come from working with the publication pipeline. We gather geoscience books, which are now excess. In fact, right now, the University of Houston is closing its little library for the geoscience students because the room is needed for other researchers. We've now got 110 boxes, 40 pounds to 50 pounds each, of geological textbooks of wonderful variety. And they are going to go to Cameroon. Cameroon. We've shipped over 100 tons now to countries all over the world. We ship to universities. And we have a problem. We have more books coming in than going out. And there are universities all over the world, internationally, that don't have good libraries. So we need, like your group, when you meet a university like St. Carlos, that was Guatemala.
Yes.
If they have a professor or a dean who says they want books for their library, we can arrange geoscience books for their library. Also, we've been successful in having oil companies very often fund the shipping. Shipping is amazingly inexpensive by sea.
Yes, it is.
So once it lands on the land, then we have to have the work with the universities. And that comes from programs like yours, where you know the people and the people really want the books. So we are always happy to learn of a new group that might like publications.
Well, then we may be able to figure out a way to bring those together.
Yes, that's what I'm
Because
suggesting.
I actually donated a bunch of my books to your library a couple of years ago.
Yeah, I think I picked them up.
No, I dropped them off, actually.
Did you? Oh, good.
The organization really, as I said earlier, is different from a lot of these other organizations. There's Engineers Without Borders,
Doctors.
for instance, and in that case, and we've actually they've been partners in a couple of our projects. But the Engineers Without Borders, usually there's a professional engineers that go to the location to help with the program. And it's so, yes, there is some funding involved, but our role, it really is to fund these projects and give seed money to these projects so that they can get their work done, their ideas done, and educate the communities. Because educating the communities is critical. You have to go in at the community level. I feel strongly. I've got a son who's involved with aid work, and he's even stronger than I am. And need to go in at the community level, because if you go in at the government level, not all the information drips down.
Any more questions? Okay, well,
On all the tables here, incidentally, and there's some out there, I've got a Geoscience Without Borders flyer. If anyone's interested, they're here. Any question?
I was going to ask a follow-up question to Jim's about the bodies versus bucks. Regarding the bodies, you've got professional geologists and geoscientists and geophysicists providing the governance of the organization itself. And then I would imagine you've got geology students, graduate students, doing the field work and work at the project level. Is there any need for professional expertise kind of in that in-between guidance type function?
We haven't figured out how to put that into it yet. And I know there's a need. A couple of our projects, there is a strong need. I recall a strong need. For instance, the one I'm thinking about is in Argentina. And they were using, first of all, for their imagery, they were using Google Maps. And I've been working, trying to get connected with Digital Globe, because the Digital Globe Foundation will provide imagery for projects like this. And they're actually providing imagery for the project that started this year in Ghana. But this one project I'm talking about had to do with groundwater. And they were finding differences in the groundwater and the groundwater volumes in different places in the area. Well, it was obvious that the high volume waters and higher quality waters, you could see the old stream channels. So they were getting these out of stream gravels rather than out of fractures, where they were having problems with getting enough water for these individual villages. And so it's that sort of thing that professionals can bring to it, people with the experience can bring to it, understanding the space, understanding the geomorphology, just from the imagery.
Can I make a comment about fundraising?
Please do. You want the mic?
Yeah, that's what I do. Live in Dallas, but come down here a lot. We spend $450,000 a year for 8 projects. $50,000 a year, some projects over 2 years. Bob said you like to have, how many you want to have? 18, 16, 24. I talked to a friend the other day, he said, how about 100? Well, that's going to be a while. But, so we need ideas. And one idea that I've been thinking of is, we've been talking about this, where if we're in a country that has oil and gas, we talk to the oil company. Many oil companies like to, like they say build schools and say roads in these countries. And we ought to at least tell them what we are doing in the country. And maybe they might help out, maybe not on an overall dollar basis, but they may help in many other ways. Water companies, I know you had some ideas about, contacting the water companies around the world. In addition, we had this recent storm here in the city of Houston, and this is not really fundraising, but how can we help the city of Houston? I think they're going to have a special surface workshop. It has to be focused, and you have to deal with the Corps of Engineers, I guess, and that would be difficult. But anyway, we really need ideas, getting back to fundraising. We had $1.6 million tied up in the overall stock market, and we would peel off, say, 3 to 4% a year. We had contributions from the APG, we had contributions from, by the way, we have a lot of contributions from the SUG members. Schlumberger is a major sponsor here for about 10 years, $200,000 every year. One oil company may come in, next year. So anyway, we'd like to make this program bigger and stronger. And so we certainly welcome any ideas and somebody what they have about fundraising.
That's very true. One of the examples Mike had, and it was not done, but it's something that once we approve a project in a place like Kenya, you've got companies like Tullow that are drilling wells over there. They would be, one possibility would be contacting these companies.
Have you extended your reach on other societies? It seems like it's a small number of societies that are supporting you, and I can think of probably 3 or 4 others that you really ought to.
We know there's 3 or 4 others, and we're working on it.
Okay.
Thank you.
How about SPE? We'd like to have SPE. Which other?
American Geophysical Union, which is very
AGU?
academic.
Yes.
AGU? Yeah, those guys would be.
Yeah, and we haven't talked to AGU, but AGU, we hope that next year there's going to be and it was first this program talking about humanitarian needs and applications of geology. There was a program that was first proposed as a Penrose conference. The GSA decided that it really didn't fit GSA, but the AGU picked that up. So we now have some connections and developing connections with AGU as well. Any other questions? Well, thank you. I enjoyed talking to you. Appreciate it.
Well, thank you for your talk about the HGS has an award for you here. Coming door.
Thank you.
Okay, the meeting is now adjourned. If you'd like to talk to Mr. Merrill, come up again after the talk. Good night.
Yes.